Alright, thanks for watching, and today I want to talk to you about the replacement theorem, which I like to call the heart and soul of linear algebra, because without it, linear algebra would not work, and it wouldn't be as nice as it is now. And before I do that, let me give you some motivation. So here's some motivation. Because what is the replacement theorem saying? Suppose you start with a linearly independent set. And let me call it lin. So let lin be 2 minus 3, 5, and 1, 0, minus 2. You can indeed check that it's a linearly independent subset of R3. Or in this case, a vector space is R3, so it's linearly independent. And how many elements does it have? It has 2 elements. That's one thing. On the other hand, suppose you have another set that you know for sure spans your space. So let gen generates, so spans, be, for example, the set 8 minus 12, 20, 7, 2, 0, and 0, 2, minus 1. And again, the reason it's called gen, not like gen Korean barbecue, which is delicious, but gen as in generates or spans, because it's the voice of my generation. Spans R3. And this has 3 elements. Then, what does the replacement theorem say? It says the following 2 things that are very, very important. So the replacement theorem says, first of all, that a linearly independent set can never be bigger than a generating set. So in this case, lin, the number of elements in lin must be less than or equal to the number of elements in gen. In particular, if this set, for example, has 4 elements, it cannot be linearly independent. That's one thing. And second of all, most importantly is, starting from this linearly independent set, we can add at most 1 element from gen to actually get another generating set. So it's sort of a way to extend a linearly independent set to get a new spanning set. And so what this says is we can add, again, precisely the difference. So n minus m, which is 3 minus 2, which is 1 element, I guess vector, from gen to lin to get a new set that also spans. Spans R3. So again, it's some sort of way to extend any linearly independent set to get a spanning set. And by the way, the statement of the theorem, it's not too important. It's really the consequences that are important. And I'll talk a lot about the consequences today. And in fact, how do we do this? Well, let's pick some element from gen in this case. 8 minus 12, 20, that's not a good element to pick because it's a multiple of this. So let's not pick that. For example, we can pick 7, 2, 0. So in fact, let H to be, again, 7, 2, 0, which again, it's a subset of gen. Then, if you add H to lin, and the way to say it mathematically is with the union, then lin union H, which is 2 minus 3, 5, 1, 0 minus 2, and 7, 2, 0. Let me just check. Yeah, that works. This thing, it spans R3. So again, what did we start with? We started with this linearly independent set lin and just added a subspace of the generating set to get a new generating set. And notice, in particular, it's better than the original generating set because sort of the head of it, or I guess head or tail, the way you see it, is actually linearly independent. One thing though, actually no, two things. First of all, this set doesn't have to be linearly independent. All that we know is that it spans R3. Also, it's not even important that it spans R3, it's really the number of elements you add that's important. Because otherwise you could just start with lin and just add all the 3 vectors. Of course you would get a new generating set. But the point is, using just one extra vector, you get a new generating set. And before I state it, again, let me maybe draw another picture. So a little proof by picture. So let's start with a linearly independent set. And linearly independent vectors, I'll just put squares. So square, square, square. So suppose, for example, in this case you have, let's say 3. M equals 3. And you have a generating set that's, let's say, with 5 dots. 1, 2, 3, 4, 5. So n equals 5. What the theorem, what I'll talk about, will say is that you can add exactly 2 dots, so 5 minus 3, to the linearly independent set to get a generating set. So for example, if, again, there will be 2 precise dots that you can pick to extend lin to a generating set. So if you have h equals to those 2 dots, this thing, again, with size n minus n, which is 2, then if you take the union, lin union h, which becomes square, 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 dot, dot, then we know that this new set spans R3. Spans your vector space. And of course there might be some redundancies. It's possible that one of the dots is actually a square as well, but we don't have to worry about that. So the point is, we do get a new spanning set whose head is precisely lin. Okay, and now let me state the theorem. I know lots of motivation, but it's very important. So without further ado, the replacement theorem, or what I like to call the extension theorem, because you're just extending. Theorem. Again, let lin be a linearly independent subset of a vector space V with m vectors, and gen be a spanning subset. Oh, it's supposed to be subset. Of V with n vectors. Then, what do we have? We have that, first of all, as I said, a linearly independent set has to be smaller than or equal to a generating set. So then, first of all, n is less or equal to n. And second of all, precisely this, namely, there is a subset of gen. So you see the red dots, they're a subset of the black dots, okay, with, again, n minus m vectors such that if you start with lin and you take the union with H, so lin union H, still spans your vector space. Okay, sorry for the messy board work, but I really want to keep that picture. So again, let me reiterate. Suppose you have two sets. One is linearly independent, the other one generates. Then, starting with that linearly independent set, it turns out you can add precisely two vectors from gen, you can borrow two vectors from gen, to get a new spanning set. A set that sort of extends lin. Because notice the first three vectors are precisely the one from lin. And that's why I like to call it the extension theorem. But why is it called the replacement theorem? Because another way to think about this, somehow what you're doing, you're taking the black dots and you're replacing them with the blue squares, which are nicer. So you're replacing your generating set with a better generating set. And again, I will not prove this in this video. I will do it in another video. Otherwise, this one will be too long. But let me show you why it's so good. Because it turns out everything we want to know about linear algebra, we can show using that replacement theorem. So now let me give you 2 or 3 corollaries from this. So, first of all, it resolves the question about, dimension. Because what is the definition of dimension? It's the number of vectors in any basis of a vector space. How do we know that 2 bases have the same number of vectors? Because of the replacement theorem. And again, the issue would be, in theory, there could be a basis for the same space with 2 vectors, or one with 3 vectors. Then you don't know what the dimension is. It could be 2, it could be 3, it could be 2.5, but no fractional stuff here. This is just pure linear algebra. But let me show you that indeed they do have the same number of vectors. So corollary 1. And we'll do it for finite dimensional vector spaces. I'm guessing it's also true for infinite dimensional ones, but replacement theorem only works for finite stuff. So suppose V has a finite basis. Then every basis of V has the same number of vectors. Okay. Why? Again, by the replacement theorem. How can we show it? So, first of all, let beta be that finite basis. And let gamma be another basis of V. And it's possible, very important, it's possible that gamma could be infinite. So, could be infinite. We never said that the other basis has to be finite. And what's the idea? It's really cute, okay? Well, beta is linearly independent. Gamma must span, again, by definition of a basis. So beta must have fewer elements than gamma. On the other hand, gamma is linearly independent and beta spans, so gamma has to be smaller than beta, and therefore they have to be equal. Great argument, I know, I'm so proud of myself, except, again, it's possible that gamma is infinite, and the replacement theorem doesn't hold for infinite sets. So, we just have to tweak this a little bit, and therefore, let's do the proof. So, suppose, fortunately I have to erase this. First of all, suppose gamma is bigger than beta. And like beta, well, it's finite. Let's call the number of elements in beta, let's call that n. So which will be the dimension of your vector space. So, well, gamma is greater than n. And again, gamma could be infinite, but we'll see that's not a big problem. So, because what do we have? Gamma is some set like that. Square, 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 square. Lots of squares. Again, it's possibly infinite. And what we want to do, well, because gamma is infinite, and because gamma has more than n elements, it has to have at least n plus 1 elements. And what we want to do, we want to choose a subset of gamma with n plus 1 elements. So let's call it gamma prime, n plus 1 elements. And so, because now we have a finite set, we can actually apply the replacement theorem. So here's a trick now. Well, beta is a basis, so it spans. So let beta be the generating set. And then let ln be that subset with n plus 1 elements, be gamma prime. Then what does replacement say? Says that ln has to have less than or equal to gen number of elements. In other words, the number of elements in beta is less than or equal to the number of elements in gamma prime, but beta has, the opposite. So gamma prime is less than or equal to beta, and therefore n plus 1, because gamma prime has n plus 1 vectors, is less than or equal to n. And in no world is n plus 1 less than or equal to n. And that's a contradiction. A contradiction with what? A contradiction with this fact. So gamma cannot be bigger than beta. So gamma is less than or equal to beta, which is n. Which is really cool. In particular, gamma has to be finite. Not only is it less than or equal to beta, but it's also finite. Okay, and which also means now we can actually apply the replacement theorem to both things. So now, well, let's switch this. So let ln be beta and gen be gamma. Then, by the replacement theorem, this one is smaller than this one. And that's all we needed, because we've shown that gamma is less than or equal to beta, beta is less than or equal to gamma, and therefore beta equals to gamma. And so, if you pick two arbitrary bases of V, assuming one of them is finite, then they actually have the same number of vectors. And therefore, the notion of dimension is well defined. So, that's pretty cool, but there's more to it. because so far we just used one condition of the replacement theorem. Let's now show other things. So second corollary. One fact that I'm sure you use all the time in linear algebra, even though you didn't know why it's true. So suppose V is n-dimensional, then any subset, so any linearly independent subset of V with precisely that many vectors is a basis for V. In other words, if you have three linearly independent vectors in R3, you know automatically that it's a basis. And why? Well, let L, or lin if you want, be that linearly independent subset. So let L be that linearly independent subset. Then all you have to do is use a replacement theorem with the following two things. Well, we have our linearly independent subset, so lin is L. And the question is, what about a subset that spans? Well, because it's n-dimensional, you do have a nice subset that spans, namely a basis. So gen, any basis of V. Now question, how many elements do we have here? Well, L has n vectors. Well, and any basis of V must also have n vectors. We've just shown this. Okay. Because it's finite dimensional. And so what does the replacement theorem say? It says we can actually add 0 vectors to L to get a generating set. Then there is a subset H of gen with, again, n minus n, which is 0 vectors. And before I do the excitement, well, what is a subset with 0 vectors? Well, it's the empty set. So H is empty, such that lin, or L, right? L union H, so lin union H spans V. But then, what do we have? Well, lin union H just becomes lin, which is your linearly independent subset. So lin union H equals to L union the empty set, which is L spans V. Why do I put check mark? Because we know that L is linearly independent and it spans V, so by definition it's a basis of V. So this is really cool. And now, do you start to see why the replacement theorem, the statement itself is not important? You don't really have to understand what it says. It's really the consequences that are super important. And I think one last one, because, well, it was a bit trivial that, H was the empty set, but I just want to show you sometimes H is not the empty set. So corollary 3, if V is finite dimensional, so if dim V equals n, equals n, which is finite, then any linearly independent subset of V can be extended to a basis of V. And this is so important, especially in particular what it says is any basis of V, or I guess any basis of a subspace can be extended to a basis of the whole space. And that's the thing that's literally used like 10,000 times in linear algebra. So here's the picture. Suppose you start with a linearly independent subset, then you can actually extend it to a basis. So in a replacement theorem, you can not only extend it with just dots, but actually squares. So what this means is you can start with a linearly independent set and you can actually extend it to a bigger linearly independent set. That's a basis. And again, why is this true? So again, by the replacement theorem, so let lin be that linearly independent subset. So good, it's a linearly independent subset. What is a generating subset? Well, all we can just use is the basis. Okay, so any basis of V, let's call it beta. And so that linearly independent subset, it has some number of vectors, let's say m vectors. And we can show that m has to be less than or equal to n. And of course, any basis, because the dimension is n, it has n vectors. So what does the replacement theorem say? In fact, this thing, there is a subset of H of gen, so of beta. Maybe let me rewrite this. So then there is a subset H of your basis with n minus m vectors such that lin union H, again, spans V. Okay, and here's something to understand. Lin, we know it has m vectors. H, we know it has n minus m vectors, okay? Now, it's possible there's some redundancy. So, if there is none, it would have n vectors. But if there is a redundancy, then it cannot have more than n vectors. It has to be less than. So, so in other words, the cardinality or the number of elements of lin union H is less than or equal to m plus n minus m, which is n. And again, that's because sometimes there are redundancies. However, here's the thing. This set, we know it spans V. No, we know it spans V, and here is a fact that I won't show now. It's not related to the replacement theorem, but fact. If you have a set that spans your space, it must have at least n vectors. So, for example, if you have a set that spans R3, it must have at least 3 vectors. Because if it has 2 vectors, it cannot span your whole space. So, in fact, any finite set that spans V must have at least n vectors. So you see, because this set, it spans V, it must have at least n vectors. So the cardinality is actually greater than or equal to n. So lin union H is greater or equal to n. And combining those two, we get that lin union H equals n. And here's another fact, so which again, out of the scope of this video, if you have a spanning set with n vectors, so for example, if you have a set in R3 with 3 vectors that spans R3, it must be a basis. So indeed, because we have that, this set spans V and it has just the right number of vectors, it's a basis. So lin union H is a basis for V. And that's precisely what we have done. This is lin, and we've extended it with H. And we have that this whole set, lin union H, is actually a basis. So intuitively, those circles become squares. So hopefully now you're convinced that the replacement theorem isn't just some weird thing that's not important. It's actually one of the most important things in linear algebra. Because otherwise, all those facts that we need to know in linear algebra won't work. So I like to call it the invisible hand of linear algebra. Alright, I hope you enjoyed this excursion into this really deep theorem. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.